All right, welcome everybody to today's Astroparticle seminar. And I'm very happy to introduce our speaker for today. She's Professor Kimberly Palladino from the University of Oxford. Kimberly got her PhD at Ohio State. Then she was a postdoc at MIT and then staff at SLAC. Then she was assistant professor at the University of Wisconsin-Madison, and now she's moved on to University of Oxford, where she's associate professor. So Kim is an expert in direct detection of dark matter and is part, as you will listen, of the LUX-Zeppelin experiment. However, she started working on ultra-high neutrinos as part of ANITA, this balloon-borne experiment in Antarctica. And I just learned today that she also sometimes works on lower energy neutrinos, like coherent neutrino scattering, for instance, if I'm correct. But then she progressively switched to dark matter direct detection, which is has a comprehensive body of work. First on MiniClean, which is an experiment that used neon and argon. Then she moved on to LUX and LUX-Zeppelin, and there she's worked on many different topics, including statistical methods of particle identification, as detector design and data analysis, of course, many searches for WIMPs and non-WIMPs like axions and axion-like particles. And in general, Kim is involved in the development of new detection techniques. So we're very lucky today to have her talk to us about a shot in the dark, searching for dark matter with LZ. So Kim, please take it away.
Excellent. Thank you so much for having me here and that wonderful introduction. Working in the field of direct dark matter detection, it's kind of fun with the title of dark matter. There's lots of common phrases and idioms that can be entertained for this, and there's some crossover to pop culture things. And so when I was thinking about what to title a talk, I said, it's a shot in the dark that we're looking for dark matter. And of course, there's a famous film of that title. It's the second film in the Pink Panther series in the 1960s, starring Peter Sellers as the bumbling and yet brilliant Inspector Clouseau. So that is where my titles come from. And there'll be a little bit of a theme, hopefully through this talk, that we've got a mystery to solve. Hopefully there's some humor, hopefully some drama. And as you'll see, there's also a little bit of tap dancing. So I'll begin. And unfortunately, well, I have my talk on a big screen right here. So if I'm not looking directly at the camera, apologies. So what are we going through? I'll talk briefly, quite generically, about dark matter candidates and what are we looking for? And then how can we look for those with the direct detection? And then I'll start narrowing my focus to LZ itself and the xenon time projection chambers, the technology that exemplifies. And then I'll be able to fill in some preliminary information on our LZ operations, which is really exciting. I used to have to just end talks with construction photos, and now I can start to show hints of the things that lead to science results. And then talk briefly about, we're barely turning on this detector. I don't have real results to give you yet, but we're already thinking about what would be coming next. So our evidence for dark matter, of course, doesn't come from me as a direct detection person, but comes from the astrophysicists. And, handpicking what I think are some of our clearest visual and strongest evidences for dark matter in somewhat time ordered sense. On the left-hand side, we've got a plot of the M33 galactic rotation curve with what is visible of the galaxy shown to scale. And if that were all of the galaxy, the rotation curve would have been the orange line. But what's observed is the green data points, showing that there is mass out to higher radius that is not luminous. It's not looking like we would attach more matter to that galaxy visually, but those few stars that we do link are moving as if there's more matter. And so this is a hint that there's more matter out there. It's not like the rest of the matter because it didn't become luminous gas and stars. But overall, as evidence for dark matter, this is a little bit on the weak side because there are numerous other solutions to this problem, some of them including modifying gravity. But this is our first hint from originally clusters of galaxies from Fritz Zwicky, and then in the 1960s from Vera Rubin in individual galaxies, saying that there should be dark matter out there. Then in the middle, starting to indicate that this isn't just matter that could be regular matter that's just for some reason not luminous. So you could think of many brown dwarfs that never turned on, for instance. We've got two simulations done in red from the Millennium simulations And two large-scale structure mapping studies from the Sloan Digital Sky Survey and the 2-degree field of view, showing this filamentary structure of what galaxies look like out to larger redshifts. And that's exactly what these simulations of just a dark matter universe would look like. So the structure kind of pops out fairly easily at these scales in these simulations. But if you're to do the simulation with regular matter instead, and only regular matter, you wouldn't get this structure to build. Things interact too much. And so when we get down to smaller structures, of course, our regular matter matters more. But at the very largest scales of the universe, the large scale structure is driven by the dark matter itself. So we know it's something new. It's not our hydrogen and helium built structures. Another picture of this that on its own is mostly qualitative is an image of the bullet cluster. So two colliding clusters of galaxies, where in red from X-ray studies are the hot gas of these clusters colliding with each other, and in those collisions heating up and giving off radiation. And in blue, the weak lensing results of mapping out the gravitational matter of these two clusters. And you see that those two blue spots are not coincident with the red spots, and that they've essentially just moved past each other. So this is two clusters of galaxies where the dark matter itself didn't stop and interact and stay in the middle. So it didn't interact with the regular matter, and it didn't interact with itself. So it's a generally non-interacting particle. Now, these are all quite general rules, but they're giving us hints about what to look for. The final, more quantitative, but on this plot, not showing different options of what is happening in our universe, comes from the cosmic microwave background spectrum, and the locations and relative heights of the later peaks in the spectrum are significantly driven by our dark matter density. And so the N density comes to about 0.3 GeV per cubic centimeter is dark matter in our universe. So about a third of a proton per cubic centimeter is dark matter. So this is the evidence we have astrophysically, what could make up this dark matter. And here's my first Pink Panther quote, which I think as a dark matter physicist, I want to immediately grab onto. I believe everything and I believe nothing. I suspect everyone and I suspect no one. There are many, many options for what these dark matter candidates can be. And since we don't have particularly clear evidence of any of them, it could be any of them, or it might not be any of them. So our options are shown over a very wide range of energy scales that we roughly break down into two categories. On the left-hand side, the lighter particle dark matter is, in fact, instead of being called particle dark matter, it's called wave-like dark matter. So these are often roughly called axions and axion-like particles. The axion, the original one kind of listed here under QCD axion, is the same one that solves the strong CP violation problem. But a very similar scalar field can be added to give other axions. There's also dark photons and more complicated versions that still give you some wave-like behavior. And it kind of changes what interactions with our regular matter there could be and how you would go searching for it. On the right-hand side of these slightly heavier options is where things are more particle-like. And so doing particle-like searches makes more sense for these higher mass particles. In the original formulation of the weakly interacting massive particle, or WIMP, it was a small range shown here, where it was somewhat really linking that density of dark matter with the scale of the weak interaction, either W or Z mediated, and now kind of down to Higgs mediation. But roughly most of these options are sometimes called WIMP dark matter because it's this particle dark matter. And if we, as a dark matter experimentalist, we're agnostic to how the dark matter bumps into the thing we were looking for it to bump into, And so we don't really also care what's doing the bumping into. So anything that can bump in to our target material that I'll talk about later and give us a signal, we can look for that. And so many of these categories do that. So if this otherwise seems a bit busy, a bit crazy, a bit not very helpful, XKCD agrees with you. And on the bottom is a cartoon from XKCD showing their different dark matter candidates over the same range of energies, where things like bees and pollen and electrons in space camouflage show up. Relating most of these, our canonical idea of dark matter is that it's going to be non-relativistic, electrically neutral, it's going to have very limited self-interactions, and we've got this density of 1/3 of a GeV per cubic centimeter. But there are numbers of these theories that are pushing those boundaries. And of course, if we want to use some sort of Occam's razor, we're very interested in dark matter candidates that fit with other theories or open problems. So since I started in the dark matter field a bit over a decade ago, there's really been an explosion of candidates and search techniques, primarily in this wave-like dark matter search, where previously it really was just the QCD axion that was being searched for. And quite excitingly, these theories have gone hand in hand with advances in the technology to use more quantum techniques to look for couplings, primarily via electromagnetism, to resonating cavities or to things like atom interferometers that are really opening up the field of dark matter, both for theorists and experimentalists. But that's not what I'm going to focus on today. I'll be sticking to the higher mass particle dark matter. So how do we search it? Well, for a very long time, we've been able to draw the most hand-wavy Feynman diagram you can imagine, where our dark matter X or chi comes in, interacts with some particles of the standard model. We don't know how. We treat it generally elastically, but it doesn't have to be. And we can read this in different directions. If you're a collider person, you read it going up. And so we've collided some standard model particles, created dark matter. If you're an indirect detection, you're looking for annihilation. So your dark matter can annihilate and then make standard model particles. And if you're a direct detect person like myself, you read it left to right, where your dark matter comes in, scatters off of your standard model particle. And if you can detect the scattering of your standard model particle, you can detect your dark matter. And all of these together are the shake it, make it, break it model. And we've got theorists who are helping bake up the ideas of what we're going to look for. So what are these different particle models to be tested? So one of the things that's really capturing our field a lot right now is the US's Snowmass process for particle physicists to set the next decade or so of our field. In the same way that the European particle physics strategy was vitally important for the collider field of what the future of CERN would be, our dark matter field is most heavily influenced by the US particle field. And so as part of that process, there's been lots of particle physicists, both theorists and experimentalists, coming together and creating white papers to help map things out. And so we get brand new plots. We really had been showing plots from the last Snowmass in 2014, and now we get new plots to show. So this is a set of some of those new plots. So these are both plots of the mass of your dark matter along the x-axis and a measure of the strength of the interaction along your y-axis, showing you where we've already excluded the data. That's what's being knocked out by the words direct detection. And what's been, where our data taking will be considerably harder is below this blue line called the neutrino fog. And we can see different models from both supersymmetry ideas and more, I don't know, orthogonal ideas about like asymmetric dark matter and low mass dark matter over here, showing where these different regions are and still how much parameter space and interesting models there are for us to probe with the techniques that are still available to us easily right now. So what do we need to do this direct detection? Well, we need the ability to see a low energy WIMP-induced recoil, which means we need a pretty radiogenically pure detector, so it has low backgrounds, and we need to have a generally low threshold, about a keV. And we want to know that we're seeing a nuclear recoil because we expect that most of our WIMP models preferentially are going to interact with the heavier mass of the nucleus. So we want to be able to distinguish between those nuclear recoils and electronic recoils, which conveniently is where most of our terrestrial backgrounds show up as electronic recoils from gamma rays and beta decays. But we want to see that difference between alpha decays and nuclear recoils. And we want to be able to do position reconstruction and what we call fiducialization. So we want to cut away the edges of our detector where there are going to be, in general, more backgrounds coming from our external environment and the other detector materials, and only look in the very quietest center part of our detector for our dark matter. And in general, we're going to shield everything from both radiogenic and cosmogenic backgrounds. So another one of these new plots coming from the Snowmass process here shows, again, our masses of dark matter and the various energies that we would give the signal just from kinematic arguments. And it tells you kind of which techniques you should use in which different area. So liquid nobles in the bubble chambers look at the highest energy events and thus the higher masses. And then as we get to slightly lower masses, the ionization in semiconductors and insulators. So this was experiments like the classic super CDMS experiment with silicon and germanium semiconductors. Then we're getting to the newer materials and newer experiments that have yet to come online with optical phonons or superconductors and superfluids and various single phonon detectors coming down in energy, some of which have a lot of links back to the original ionization semiconductor studies. So what I'm going to focus on are these liquid nobles experiments. So what are the techniques, instead of just showing it in that image, we can actually think about what the experiments themselves look like to see these different events. And this is coming from the APEC direct dark matter report, where we can have a crystal target viewed by PMTs looking for scintillation lights, such as the Dama Libre experiment. We've got, again, another crystal target where we've got a thermal bath and a TES, and sometimes some scintillation observation too, like in CREST. We've got a 4-pi single phase liquid target, like in Deep 3600. We've got our 2-phase detectors that I'll go into more detail for our time projection chambers for liquid xenon and liquid argon. We can have bubble chambers with a liquid target and a buffer liquid, and where the detection comes both from images from a camera as well as acoustic sensors. And we can have gaseous detectors, or gas TPCs, which can reconstruct a drift direction. So what's the status of our field? Now, this is a very busy plot. So I'll take a second to talk about it because one day we'll finally talk to Nike and get some funding, but they all are these Nike swooshes of exclusion limit curves. We saw this a little bit before in where in that model plot, but again, our dark matter mass is along the x-axis, and our y-axis is our dark matter nucleon cross section. And this is going to be really our spin independent cross section that allows us to compare most of our targets against each other. And so where things have already been excluded is shown in gray and the solid lines. And the experiments that are essentially funded and underway have these dotted and dashed lines where to get to in the future. And we now have different shadings of what are neutrinos creating coherent elastic neutrino nuclear scatterings that are going to look exactly like our elastic scatter from a dark matter particle, created at higher energies from atmospheric neutrinos from cosmic ray interactions in our atmosphere, at lower energies from solar neutrinos coming directly, where this peak here is from the boron 8 solar neutrinos. Depending on how you talk about it and what your search technique is of being able to see, to still tolerate certain numbers of these neutrino events while still looking for an excess of nuclear recoils from dark matter we have these different contours here. And so you can see that our current limits are up here, just past the xenon 1 ton line, with an updated Panda X line actually hasn't been added to here. And the experiments coming online now of Panda X 4 ton, LZ and xenon N ton, and then DarkSide 20K a bit later will come online, will bring us to these further lines. But you see, we're still not all the way down to our neutrino fog of events. And that's where we would like to go. And we're pushing both at higher mass and higher energy, as well as lower mass and lower energy. And these two directions to push our sensitivities, push us to different technologies to achieve those. And that's essentially what we saw in that previous plot, that this can be dominated by the liquid nobles and bubble detections, and cryogenic crystal detectors can work well right here. And you see we're still cutting off of energies, I believe at a few keV. I do my math. So how does the liquid xenon time projection chamber work? So we've got a right cylinder, so it's about the same height as it is wide. And we line the edges with Teflon, which is nearly magically almost 100% reflective to our liquid xenon wavelengths when it's within liquid xenon. And we have electric grids, so basically metallic plates of meshes at the top and bottom that let us set up drift fields such that we can drift electrons up to the top of the detector. And then at the top of the detector, this is called a two-phase TPC, there's gas, and we pop the electrons out of the liquid into the gas. And in that gas, there's a strong enough electric field that they undergo electroluminescence that gives us a very bright signal. And so when our particle first comes in, we get a flash of scintillation light that not so creatively is just called S1. Then we wait the amount of time it takes to drift those electrons up, which is why it's a time projection chamber, because the time actually gives us the depth into our detector that the interaction occurred at. And we get a larger signal, the S2 signal, that becomes a count of how many electrons were emitted. And different particle interactions will give us different ratios of this initial scintillation light to this ionization light. So this is what the basic detector looks like. We get our Z position from this timing, and in analyzing the S2 light in the top, we get the XY positioning of the event. So maybe this is a good point to pause after talking a little bit about theory and a little bit about the general physics of the detector, if anyone has a question.
Yep, Marcus.
Yeah, quick question. So you had this overview plot with the different blue colored shaded regions, and you mentioned this is from the neutrino floor, this one here, yeah.
Yeah.
Can you, I see here from the legend, this is some complicated measure here, minus delta log sigma. Can you say something about this 1, 2, 3 scale?
Yeah, so what we see is that because of the relative nuclear terms, argon experiments can go a bit deeper before they start to see these interactions. And so that's what this dotted line, for instance, for argon is. And so to show that it's not just about this initial line, but it's really a whole feature, this is somewhat saying, you know, how many extra events. So, the very top of this line is where you're going to see one neutrino event. And you can see that both LZ and xenon N10 are going to, be at the edge of seeing one neutrino event, and we're likely going to see a few from the boron 8 interaction.
I see.
But that doesn't mean just because we've seen a neutrino event and we're not going to be background free in our nuclear recoils, that doesn't mean that the technique is dead to continue looking for more nuclear recoils. And that's what is being captured, so that you could do still a 3 sigma discovery experiment with down to these cross sections for particles of this mass, even with even with more backgrounds from the neutrino interactions. Does that make sense?
Yeah.
Sorry, my phone just started to ring. Okay.
Thank you.
So there's a question by Victor. I don't know if Victor, you want to ask it yourself?
Yeah, I can. Can you hear me?
Yeah.
Okay, yeah, I can read it out loud. I was wondering if the neutrino fog limit is a fundamental indistinguishable signal, or if it's any way to avoid that noise to distinguish if it's a dark matter candidate, or you can tell for sure that it's a neutrino interaction.
So on an event by event basis, they are indistinguishable. They're just going to be a nuclear recoil of your nucleus. But if you have statistically enough events to study, it's why our gas TPCs are of interest, because they can be directional detection. And so since our planet is traveling around our solar system in our big WIMP halo, our dark matter halo, there's a preferential direction for the dark matter events to be colliding into us. And so this is called kind of the WIMP wind or dark matter wind. They would be preferentially coming in one direction. Now, mind you, these are really low energy collisions. So you need a very low threshold detector, and you need to see enough of the signal to find the direction that your recoil happens in. Right, you can picture, right, this is elastic recoil. So, you need to, imagine in your head your two body collisions and the angles that are accessible to it based on how much energy. And so, on the orders of tens, if you had tens of events of dark matter, you could start to pick it out from the neutrino background. Now, the problem is that we still don't have any events for our nuclear recoils for dark matter searches. And the way we're searching is by going to larger and larger target masses. And the techniques so far that give us this directionality currently don't let us access those masses. Now, when our techniques kind of hit that floor, we'll, I think, be asked that question, is it worth continuing to look? And is this directionality search the only way to do it? And I think then more people and more money would go into this field to develop it more fully, to try and get through the neutrino fog. But I think we'd all be evaluating whether it's worth it. So for a long time, there's been the drift collaboration, and now it's joined with the other directional detection experiments to be like the Cygnus consortium of experiments that would lead directional detection in the future. But right now, they're not really competitive in these raw limits. But that is how you could do it. But you need statistically significant numbers of events.
Thank you.
I have one quick question about the design of LZ. I was wondering, where are the PMTs? Are they on the lids, or do you put them on the sides?
Yeah, they are on the top and bottom. So these devices up here, top and bottom, are our PMTs. So we've got 494 of our main TPC. They get shielded from the high voltages of our chamber, and that's why we needed that light collection from the side. So preferentially, a little bit, our S1 light goes to the bottom because of total internal reflection off of the liquid surface. And when our electroluminescence gain is so high in the top of the detector, actually sometimes for the very highest energy events outside of our WIMP search region, our best reconstructions of energies for kind of like high energy alpha backgrounds can come from just looking at the S2 light that makes it back down to the bottom when we saturate PMTs at the top.
I see. Yep. That was yeah. Thanks. Now that explains it. I don't see any. Yeah, go ahead.
Oh, no problem. I'm just sorry. Can you see my message or not? Okay. Sorry, I had to my that call that I hung up on was my son's day camp saying that he has to be taken home. So my husband is doing that, but okay. Sorry.
Sure, no worries. I see all the hands, so I think we can go on.
Excellent. Okay. So our LZ experiment here is a hybrid meeting where we had groups meeting in person in the UK and in California, but our national labs in the US, which weren't allowed to travel but could meet together, and then everyone else still joining us remotely. So we've got about 35 institutions, 250 scientists, engineers, and technical staff. So I'm really speaking now on behalf of all of them in talking about our detector and our results. The LZ experiment is located at the Sanford Underground Research Facility in Leeds, South Dakota. It's the old retired Homestake gold mine that the gold is discovered at the very final episode of the old HBO show Deadwood, and is one of the deepest mines in the US, but it fills with water. So it was a mine down to 8,000 feet, but currently our experiments are located at the 4,850 foot level. LZ is located in what's called the Davis Cavern, where both LZ and the neutrinos double beta decay Majorana demonstrator are. And over down under another shaft, the Ross shaft, is where excavation is happening for the Dune experiment actively right now. Our Davis Cavern is where Ray Davis had his solar neutrino detection experiment. So it's a fairly illustrious place to be able to operate your detector. And this is what our LZ detector looks like next to a person for size. We see that main TPC, which is only 1.5 meters in height and diameter. And then surrounding that, we've got a cryostat. We then have veto systems inside the liquid xenon, but outside of that main TPC, we have small 1-inch PMTs and some 2-inch PMTs at the bottom that look at what we call our xenon skin. This is separating the high voltage of our detector from the cryostat metallic walls, but are another place to catch multiply scattering gamma rays and neutrons. Then we come out to our main veto detector, which is gadolinium loaded liquid scintillator inside acrylic vessels that are observed by PMTs that are then out in water, which are enclosed in more water, all to shield us from the radiogenic backgrounds of uranium and thorium decays in the rock of the cavern itself. And we need cabling and subsystems to get down into the detector. So we have instrumentation conduits to bring in our cabling and systems and other systems to carry our xenon and gas system monitoring. Similarly, we bring our high voltage for our cathode in horizontally. This was a major improvement over the previous detectors where the high voltage ran down along the side of the detector and made it really hard to achieve the high voltages that we'd want to set up our drift fields. And then we have our bottom PMT conduit as well, our bottom signals to our PMTs, as well as our liquid xenon system. We are constantly recirculating our xenon because of essentially emanation from the plastics of essentially just air and all the things that are in air, but that also can include radon, that the gases produced when something in the uranium or thorium chain decays in our metal. And this can be removed if we purify our xenon, and we still do that purification in the gas phase. So we pull out liquid xenon from the top of the detector, warm it up to become gas, send it through what's called a hot gas getter, and return it, and it removes essentially everything that's more reactive than a noble. And then we re-chill our xenon and send it back into the detector at the bottom. Having that plug-in to our liquid xenon also allows us to put in radioactive calibration sources as needed. So if you go to see that now, of course, all you see is a large metal cylinder. So all there is to see now essentially is that water tank. But what went inside, so these are our high voltage grids. We actually discovered that at this large of a scale, if you ran just parallel sets of wires, they would put such a mechanical strain on whatever is holding them that it would kind of potato chip in shape. And to avoid that, we wanted a woven grid, but there were no commercially woven grids available at that side. So like a mesh, like just screen materials. So in a clean room at SLAC, our own custom made grids were woven. And here you can see the joining of the top part of the detector to the lower part of the detector. And with the light shining, you can see some of those woven wire grids. They're, very thin, very pure wires chosen because we want to maximize our transparency and getting all of our light to our photomultiplier tubes. Here are two arrays of photomultiplier tubes. And again, we have a Teflon even between the faces of all of those PMTs. And so here on the left, this is our top of our array. And you'll see we start off being circularly symmetric at the very edge to reconstruct the wall of our detector, but we get to better close packing, hexagonal packing inside the detector. And so there's kind of a transition zone right here you can see in the pattern. I like this picture because you can see some of our low mass cables wired up on the back. And that's what one of the things my group had made at the University of Wisconsin was 19 kilometers of cables cleaned and high voltage tested. So here's our full-time projection chamber on the left-hand side. On the right-hand side, focusing in on the kind of most impactful part of our detector is the top. We happen to call it the top corner because when we do that profile, it shows up just as the corners. And so here we have those 1-inch PMTs that are going to look outside the TPC, along with routing of their cables up and over the high voltage region of that extraction region where we pull out the electrons. That's also where we have to maintain our liquid level height. And so we do it with a Weir spillover so that, there's just essentially a hole and the liquid can flow over that. So in 6 different locations. And that's mapped by these peak pieces. And this is a Weir drain line coming down for our detector. We've got a titanium cryostat where titanium is chosen for its low radioactivity, really reducing our backgrounds compared to stainless steel detectors that have been used in the past and are used by some other experiments. Here is the bottom of the outer vacuum vessel. So the outer vacuum vessel, inner vacuum vessel. Here it is sitting inside its water tanks, and it was a choreographed dance to bring everything in. Here we have our source deployment tubes that are going to run down along the side of the detector to allow us to lower primarily gamma sources along the edge of the detector. And these are some of the still covered in plastic, the acrylic vessels that are going to hold our neutron veto scintillator. So now I'll get to actually the more fun and exciting part is talking our preliminary operations. And all of this is coming from, it's other publicly available information that was given at the UK's IOP talks and the APS April meeting. And so in the Shot in the Dark movie, there are 2 famous scenes where there need to be distractions for the audience. And in one, in a very 1960s style, Inspector Clouseau visits a nudist colony and appropriately holds a guitar to keep anything interesting hidden. And in another scene, a murderer is at a flamenco dance and times his shots to match the tap dancing of the performers. And so again, hiding his shots. So this is to say, I might not be able to answer all of your questions on what I'm showing because we're still taking our WIMP search data, and these are just preliminary results for our calibrations. But they're going to give you a sense of what we know about our detector and how it's performing. So of course, one of the very first things we need in giving this is knowing that we're capturing our light correctly. We understand the data that was coming in. Our PMTs are working correctly. And so one of the first things that's somewhat interesting in our detectors is that our xenon light is in the vacuum ultraviolet. And so it's so energetic that in fact, we don't just get regular photoelectric effect, but we can get a double photoelectric effect that the initial electron essentially can have so much energy still on the photocathode, it can knock out a second electron. And this is great because it gives us a PMT pulse that looks like the data shown here that's fit with a single photoelectron Gaussian and a double photoelectron Gaussian, giving you the summed total pulse here. And so that means that we don't just count our kind of, the regular charge seen on a PMT and relate that directly from the single photon image to the number of photoelectrons seen, but we convert it, the total number of photoelectrons seen using this ratio of these 2 peaks to the numbers of photons initially detected. So for instance, a lot of other experiments use photoelectrons and PE as their unit of measurement, but we use PhD counted as photons detected. This has allowed us in the past on the LUX experiment, and we anticipate in future analyses on LZ, getting to use this effect to go to lower thresholds. That one of our real energy thresholds of the detector is essentially dark noise and other coincidences in our photon energies. And so we anticipate from our sensitivity studies having a threshold of 3 PMTs seeing our light, but maybe we can reduce that to 2 or even 1 if at least one of them is seeing two photoelectrons that had to have come from UV light and not from another visible light source that could be creating light in our detector, but is not VUV and so not able to knock out 2 electrons. Our data, for the first time, our collaboration moving from the LUX experiment to LZ has to have a trigger. We previously operated in untriggered mode, but more importantly, we always did operate in a zero suppressed digitization mode, and that's what's being shown here. So pod means pulse only digitization. So we had to create a more complicated data acquisition system, and then to diagnose and make sure that that data acquisition system is working correctly, we have the ability for a limited amount of time, mostly because of disk space, to take data entirely unzero suppressed and untriggered, as well as our regular data. So our regular data stream would have PMT pulses like this blue line and this green line, and we don't save the data in the middle. And so we have to run a significant number of diagnostics to make sure we're not losing any information in doing that. But this allows us to take very long data samples of 4 microseconds is how long we keep the data as we look for both our initial S1 pulse and our S2 pulse. Our triggering is on our S2 pulse in the main TPC, and there are other triggers for the skin and for the OD. And all of the detectors data is read out at the same time if there's a trigger in any of one of those systems. So this has been checked out and is working well. So besides just checking that our main detector is working correctly, we want to make sure that our veto detectors are working quite well. And our outer detector's main job is, by including gadolinium, going to capture neutrons. And so tell us if that neutron had an elastic scatter inside the TPC, but no other scatters and no capture there, we can capture it on the gadolinium. And then tag that nuclear recoil as being a neutron and not dark matter, not a neutrino. So our background data in our outer detector shows up here in blue. When we put neutron calibration sources, we see a lot more light. Not only do we have this higher 8 MeV gadolinium signal, but even just capturing on regular hydrogen gives us another peak in signal. And so as we can set thresholds below this to see these events. And so on the right-hand side shows what this overall background scaling is and where our threshold is. So our threshold at about 40 photoelectrons, down here on the right, on the left-hand side, here on the right-hand side, gets us our trigger. We really set a requirement to be triggering the outer detector less than 100 hertz was the red dotted line, was our overall requirement. This blew up a little funnily and switching to PDF, sorry about that. So this is, we also have to calibrate our detector, and we want to make sure that we understand those nuclear recoils that we're looking for. And one of our best ways of doing that is with a monoenergetic neutron source that comes from essentially a very mini particle collider where we accelerate deuterons into a deuterium impregnated foil and have a DD reaction that gives us a 2.45 MeV neutron. So we have a special conduit so this little particle accelerator DD generator is outside the water tank. We have a conduit running through our veto that we can fill with water when we want to shield our detector from neutrons, but when we want, we can evacuate it when we actually want to take neutron calibration data. So we evacuate that that conduit, and the line that those neutrons would come through, coming through that conduit, is shown here by these orange dotted lines. And so we see these neutrons coming in. So this is in, the XY plane. You can see it kind of looking down from above what these neutron events look like. The red dashed line is our rough radial cut of, we'll look for dark matter events within that circle, because outside of that, we get a lot more radioactive events from the edge of our detector. Basically from that Teflon wall, there's a lot of radioactive decays. Things just like dust have uranium and thorium in them. Okay. And then slightly unfortunate, in the future, we might plan differently. You can see in our X versus Z where our neutrons come in, and they're at the very top of the detector. And so this is helpful because it means we can do these calibrations when our detector is not very pure. And what that means is that if there's electronegative impurities in our detector, electrons will attach to them. And so if we were to do this calibration at the very bottom of the detector very early in our runs, then we wouldn't necessarily get our full S2 size to get the calibrations of our nuclear recoils. And so it's useful to do it at the top, but we did it so high at the top, it's very close to where all that extra material is, so it's going to be outside of our fiducial bound because there's still more radiogenic backgrounds there too. So it doesn't, with just this one neutron source, we don't really radiate our whole detector. One of the really amazing things that is done with this is that, so we start with a monoenergetic beam, but again, we're looking for these elastic recoils. So each recoil is going to be a different energy. We can actually, besides our very clean events of all events here, when we've got very high statistical runs, we can look for multiple scatters where we can measure the angle between our first neutron-induced recoil and our second one, and then know the precise energy that was deposited in that first one, and get very high precision recoil information for our detector. So that's a high precision calibration that we are very interested in completing in the same way that the Lux experiment did. So we put a lot of these things together. And so besides knowing that our PMTs are working, that we can calibrate events, we need to know that we can get our energy calibration correct. One of the things we can do is make what's called a Dokay plot for the Japanese scientists who first made it. And it lets us look at a number of different sources, both calibration sources that we've lowered in or injected into our system, as well as naturally occurring isotopes, as well as cosmogenic activation ones that came from our xenon was purified at the SLAC National Accelerator Lab in California and then shipped by truck to South Dakota. And so it only went underground a few months before we turned on the detector. And so from the cosmic rays hitting it as it went over the Rocky Mountains, we have all of these higher energy, these xenon lines that are going to decay away. They've got decay lengths of about a month. So we won't see them in future runs, but in these earliest runs, we've got multiple peaks, and we can line them up and tell us how much of our light we see. So we see between 10 and 11% of our S1 light, and looking just down at the bottom of the detector, because many of these are higher energy events, we get 13 photons per electron. And that's about 40 to 50 photons in the top detector. So we understand our energy resolution, well, our initial energy as well as its resolution. And now we can look at that difference in our S1 and S2. So S1 is going to become our proxy for the overall energy on the x-axis, and the y-axis, we're using this relationship with the S2s to give us our discrimination against electronic recoils. So our electronic recoils here from lead decays later in the radon 220 decay chain. So we put in short-lived radon 220 and see electronic recoils from the beta decays in the lead. And we've got that DD nuclear recoil spectrum here, where not shown is the very lowest energy electronic recoil data. And this is kind of before data quality cut. So it's quite preliminary. And in fact, it's taken so early that it's not quite the run conditions of our whole WIMP search. But these are the types of studies we do to see that we do indeed have discrimination. Now, we don't do a simple cut and count analysis, but we put both of these profiles that are very well studied into our profile likelihood ratio machinery in determining if our data set looks like it has any dark matter nuclear recoils in it. But even if we were to do a plain cut and count experiment, you can see that below the nuclear recoil mean down here, there's very few leakage of any electronic recoil events. In fact, our understanding of these profiles is so well done that we actually do better fits of what our light collection is by studying these bands than we do by looking at all of these different sources as we had in the past. I'll try and speed up a little. Radon is one of our main backgrounds. It's because of this lead decay later that is a beta decay. Sometimes it's got an associated X-ray and we get a multiple scatter, but sometimes it's what we call a naked beta. Another, I need to work out the joke for that to go to the Pink Panther movie, but so we've got this naked beta that we worry about. It's about 2/3 of all of our electronic recoil backgrounds. And one of the things that came from the XO200 neutrino stable beta decay experiment that also has a xenon TPC is studying the decay in that radon chain between two different alpha particles, the radon 222 one and the polonium 218. And so they happen, I'm going to get the time apart, like 50 seconds apart, I believe. And so our detector liquid hasn't moved too far in that time. And we here are looking at mobility. Now, electron mobility is velocity divided by field. Field is given in volts per centimeter, and so that's why we have centimeters squared per second per kilovolt. Is the multiplication of those two values. And we see that a lot of our polonium is here with no mobility, and we see a whole bunch here with some higher mobility. And that's saying that these polonium daughters were created neutral, but these are all charged. And since they're charged, they're going to move in our electric field. They'll come up to the top of the detector, and there'll also be some of the easiest ones to remove in our purification process. And so our from the literature, which is essentially the XO200 experiment, they had a charge fraction of 50% and a mobility of 0.21. And we're getting very similar results in this preliminary data set. So again, we're seeing that our numbers of lead decays is not going to match one-to-one to our rate of radon decays because we have these chances to remove the other radon daughters before we get to it. Here, using those G1 and G2 values, we have some reconstructed energies of higher energy background and calibration sources. So you can see this is still quite preliminary. So our peaks at our lowest energies line up quite well. They become further off as we get to higher energy, and that's essentially due to saturation effects, which will have to be solved when we want to do things like neutrino stable beta decay analysis, but don't affect our WIMP search energy regions, which is really down here essentially. So this is what our preliminary background model looks like. We monitor a lot more backgrounds, and we'll need to do so for 1,000 days over a 5-year WIMP search. But for our initial commissioning data, we don't have the sensitivity to many of those. And so you can see we're dominated at these lowest energies by, we've got the lead 214, xenon 136, and the xenon 133 dominating us at the very bottom of the tail. And you've got these nice peaks to get our energy reconstructions with. So I'll try and hurry up and say, this is beautiful, but what comes next? Well, we're waiting while the LZ detector is up and running right now. So too is our competitor, the xenon and ton experiment. It's got 5.9 tons of liquid xenon. It's been operating since September at Gran Sasso in Italy. And really one of its very impressive results is their reduction of their radon and krypton using a cryogenic distillation and custom pump. And they've got example waveforms that are really showing how well this radon reduction system is going in their their operating detector. So besides waiting for a result from LZ, we're all excited to wait for a result from xenon N10. And that goes into the first of the two real mysteries in the direct dark matter field to follow right now, which was that the precursor to the xenon N10 experiment was xenon 110. And it had an excess of low energy electronic recoil events. So this was essentially their initial background model shown in red, their data shown in black, and you see this excess of events right near threshold. And a lot of discussion is happening over whether this could be new physics, or is it less interesting physics like tritium or argon-37 contamination. Both of our experiments should be able to comment on it, except as you can read in this LZ archive paper, because LZ brought its xenon underground so late, we have to wait for the cosmogenically created argon-37 to decay away. So we will have an excess that's known and quantified for a bit. The other main mystery is if you don't have discrimination for your nuclear recoils, you'll have an excess. You can look for a modulation of your event because of that same reason of Earth going around the sun. Sometimes you're adding some energy as you move into the dark matter, and you sort of lose energy, and thus if you're near threshold could lose events if you're moving with the wind. And this can give a modulation signal that was observed to 13 sigma by the Dama Libre experiment. It's been ruled out both as a raw signal shown here in two different interpretations of their data sets by the xenon experiments, especially when they've got discrimination against between nuclear recoil and electronic recoil events. We haven't seen it in our electronic recoil events either, but maybe xenon isn't the right target for some more complicated dark matter model. In such case, you need to go after it with the same target this was, which was sodium iodide. And so the Cosine and Aeneas experiments are doing just that. They have got lower backgrounds and have discrimination, and as such, they are still starting to rule out Dama Libre, but not yet fully in running. They just need more time to keep running to collect more annual cycles to do an annual modulation search. So those will be interesting results as they come out too. For this very long-standing result, this summary was 4 years ago, but the result is even longer than that. But longer term, we're not just waiting for these two results, but what we really want to do long term is find dark matter, measure its properties, understand it fully. And so we can scale up our current technologies from the size of LUX to the size of LZ to a future generation 3 xenon time projection chamber. And to this point, the xenon N10 and Darwin, that was going to be the follow-up to xenon N10 and LZ, are in discussions to unite for a future experiment together as a collaboration. And so we're working towards that. One of the things that becomes interesting is then, well, we've already talked about the fact that we'll see these atmospheric neutrino events. How much of a problem is it? And it's not too terrible is the answer, showing what our discovery limit of, I think this is just a 3 sigma discovery in this case, at different levels of uncertainty in our rates of atmospheric backgrounds would be. So we can still make discoveries even in light of neutrinos. And here's another picture of this evolution of the detectors that the NSF has had US collaborations on the xenon collaborations historically. The UK was involved in Zeppelin experiments before joining the LUX experiment and giving us LZ. We hope in the future to have another meet. We had our first joint meeting last spring in April. We've been having other joint meetings on approximately a monthly basis. And next month, we're going to get finally to have an in-person collaboration meeting together. The science reach of such a new detector doesn't just focus on WIMP dark matter, but can do physics actually with those neutrino backgrounds. We can also, with the xenon 136 and 124 isotopes, look for neutrinos double beta decay. And so it really becomes a rare event observatory where by far the most interesting thing it could see is dark matter, but there's still other science to do with the big detector. Here's kind of the broad spectrum of different things it can do. But as we're running late, I'll try and hurry up. I just wanted to end the talk saying, of course, that there's more than dark matter in our world. And my cryosat might be a vacuum, but I'm not. as we built our detector, I'm a hardware person, and I, didn't get to be there underground as we commissioned it due to travel restrictions. My mother came and stayed to watch my children when they couldn't be in nursery. And while all this is happening, there's other things happening in the world too, and our communities need our support. And we can work various ways towards social justice and towards improving the world situation. So on a more hopeful note, our LZ and xenon N-ton have started that science data taking. They're going to be the most sensitive dark matter detectors to date. But what's going to happen in our field after 2025? Let's make sure we get to that neutrino fog. My very rough hand-wavy calculation based on theory ideas, available parameter space, and confidence in the WIMP paradigm, it says maybe there's a 3% chance of finding dark matter in that time frame. So besides doing that, let's also explore some neutrino physics. And of course, what I'm working on in these detectors is just attacking one part of the puzzle of dark matter and neutrino physics. And it's very complementary to all of the other direct, indirect collider searches and neutrino studies. And quite personally, I really muse that the dark sector should be as diverse as our own known sectors. And so hopefully there's multiple candidates for us to discover. We'll have to go a little bit deeper than all of our main plots because we're going to be sharing that dark matter distribution density between them. But I think it's going to be a really exciting place to work for the future decades. Thank you.
Thank you very much, Kim. This was super interesting, especially for people that are working mainly on theory like me. Seeing the hardware side of things is always fun. So is there any question in the audience? I'll get started then. I have one question. It was on your slide 24. And where you were talking about saving the full data, not just the triggers.
Yes.
Yeah, on the right. So one thing that came to mind is some experiments are able to look for sub-threshold signals because they store the full data set. But I was wondering, does that even make sense in an experiment like LZ? Is there any such thing as a sub-threshold signal that makes sense?
Well, there could be. So that's what I'm saying. So we don't save everything right now. We do save these things that we call pods. It's a convenient name for this pulse. We just usually we just save the blue and the green. So you could look for sub-threshold. We are triggering on our S2s, which are very large. And in fact, our analysis threshold in S2s is essentially set by our ability to do the position reconstruction in X and Y to make sure that events are far away from the wall. So that sets a threshold of a few hundred electrons to be, sorry, not electrons, few hundred photons, and just a handful of electrons. So we've got this rolling over threshold from that, and this rolling over threshold from our S1s where we've assumed 3 PMTs need to see the light. But we've got a small number of other, so you could imagine maybe we could do a very short run of down to like lower thresholds, and we say something about our position reconstruction and other things. We've got a small number of events that aren't triggered by our TPC because they're triggered by one of our veto detectors, or by, we do have kind of random heartbeat triggers also that let us understand our noise environment. So you could include those in an analysis, but understanding our noise and our accidental rates is a significant portion of what this early commissioning science run is. And so what we could do with that data scientifically, I think will come in the future.
Yeah, thank you. Do we have questions in the audience? Marcus has one.
Yeah, one question, maybe a little off topic now, but you mentioned your diverse scientific program. I guess detection of galactic supernova might also be on your list of topics.
Yes, so the xenon N-ton experiment is already a member of SNOOS, the supernova early warning system. LZ is not, mostly because we didn't have a strong enough study of our noise and ability to see things yet. I think we're working towards where we would receive their alerts but not send out alerts probably. So we certainly can, and there's our University of Rochester group is the one most involved in the analyses to do that. So we've got different, currently even in LZ, we've got different science working groups. The main one is, of course, the low energy nuclear recoils for dark matter searches. But another one is time-dependent searches. And so those would allow you to look for burst events like supernovas, as well as just, checking annual modulation studies, both in the nuclear recoils and in the electronic recoil excesses. And since both of these rely on a very stable detector that's well calibrated across all times, the Rochester group is our lead electronics group. And so that's why they play such a heavy role in that also.
Okay, thank you.
All right, so let me ask one a kind of exploratory question that came to mind also. And this is about these alternative detectors that don't use your technology or any TPC kind of technology, which is these paleo detectors, or even these DNA strand detectors, where you break one part of the chain and then you PCR the whole thing. So what is the actual status, other than them being cool ideas of these things?
I don't think that the DNA one has come too much, but I think the idea has had people start thinking. I have not heard much new advance on the directionality detection. The other directional detection is using light nuclear emulsions. They send up these things to space. They've used them in kind of the neutrino detectors, kind of part of OPERA. And the idea is that you would put it on a rotating trolley so that it would track with your dark matter wind as over the course of the day, so that, because you're going to have to study it later. It lets you get to a bit higher mass. I'm not sure. So part of the directional study problem is that you need even more events if you just have a line and you don't know which is the head and which is the tail. And so the gas TPCs can give you head to tail, usually not as low as their threshold, but to some area. I think these other technologies don't give that yet either. So it makes it a really hard thing to want to work on right now. I think continuing to work on these ideas and continuing to come up with other things you could do with this to develop it enough to get it to dark matter is interesting. And so, maybe one of the reasons I work on this experiment Ricochet that does coherent neutrino scattering at the ILL reactor, it uses two different technologies, one kind of going to low threshold with germanium detectors led by Julian Ballard from Lyon, kind of expanding on the Edelweiss and super CDMS technology. And one side using technology that's developed by Joe Formaggio at MIT, using superconducting zinc crystals, is this hope that if we can put these detectors in a very high flux environment and that with higher energies and actually see something, that gives us enough time to keep working on these technologies to improve them, maybe for a dark matter search.
That'll be super cool. Either way, either for the current purposes or for dark matter. Yeah.
I'll say on some of the more creative things, because we've been living in these pandemic eras, there's been so many canceled meetings and talks, and so much R&D got interrupted, at least during the first year of the pandemic. I think that the conference run this summer will fill us in a lot of how far people have gone and what they're doing. I think that the Snowmass process is definitely showing lots more interest in more techniques. Most of these new techniques are also conveniently significantly cheaper than our big detectors are, because they're kind of tabletop in a lab, one or two research groups working together projects. I think that the wave-like dark matter ideas have gone the furthest. The particle ones become hard. There's just kind of, you're maximizing your interaction rates, you want something heavy. If you're minimizing your thresholds, you want something light. And that sets the bounds of what you're able to do.
Yeah. All right. So keep an eye out, people, for the conference.
Yeah, there might be something exciting I know nothing about because they've been in a lab for 2 years doing amazing things.
All right. So I don't see any other hands. So thank you so much, Kim. As usual, this was great. And best of luck coming back to in-person conferences. And thank you again for your time.
No problem. Thank you.
Thanks, everybody.
Thank you.
Bye.
Bye-bye.
Bye-bye.